give it a second. Alright guys, sorry. So you should have that in front of you, right? Constant velocity literally means the velocity doesn't change. So we're looking at a constant velocity function, we have a flat line. Now, tell me, if 5 seconds elapsed, and your velocity was 50 meters per second, how far have you traveled?
How many seconds about?
What is it?
250.
200. So if your velocity, did I say 10 or 5?
5.
Okay.
50.
Let's just write it down. If your velocity is a constant and 5 seconds have elapsed, how much position have you covered? 250 meters. Now, how did you get that? I know this sounds ridiculous because it's trivial. You guys have done this, but appease me for now. How did you get that answer? What did you do?
You multiply the velocity by the time.
You multiply velocity by the time. Everybody agrees with that, right? You all agree with that. So do me a favor. On your graph now, label 5 seconds, please. And let's label this height of velocity as 50 meters per second. So if I'm going 50 meters per second for 5 seconds, this is how far I've gone, right? How can I represent that geometrically? Using this graph, how can I show that geometrically? And I'm starting with a simple example for now, and we'll get to more complicated in a moment. What do you think? How can I represent it?
Well, yeah. Well, I remember for integrals, don't you think that the area of the curve?
Yeah, very good. So Kara's already on the right track with the area of the curve for integrals.
Yeah.
So Kara, you want to specifically talk about this one? Up until 5 seconds.
So since it's a straight line, then the integral is a square, a rectangle.
Very good.
And the area of a rectangle is length times, yeah. So you just do that and find the area of a rectangle, and then that value is x.
I think we had like 1 or 2 homework problems that like had this
On your calc or in this class?
in this class.
Did I really?
I think so.
I don't know.
It was like a triangle.
Yeah.
Interesting. And it asked you for the...
It was like a triangle. And I think
So those problems could have also been derivative problems, if you remember. They could be the slope of the line also. It wouldn't necessarily be... Hey, if you did, that's okay. We're gonna get
This
to
was
it.
in pre-calc with like the summer course pre-calc too.
And you took it in some-
Yeah.
Good. So if you've seen this idea in calc or in pre-calc or at some point along the way, that's a really good starting point. Now, if you haven't, don't worry about it. Don't worry at all. Chris, you focusing? Okay. I don't know what... Okay. Just make sure you're looking up here also. Yes, I don't know. Make sure. So we've got a base length of 5 for the rectangle. We've got a height of 50. Everybody sees that? The base is 5, the height is 50. And it turned out that 5 times 250 gave, 5 times 50 gave us 250. So it turns out that the area underneath this velocity curve gives us our, what word can I use for this?
Position.
Position change, let's use. Position change. Because where did I start? Do I know where I started on that? I have no idea. All I know is that I have a given velocity to start. But I could start at the origin and then move 250. Or I could start 10 meters past the origin and move up to 260. But my change is what's happening. So really, what I'm getting here is my displacement, my change in position. So what I'm recognizing is that the area under a V versus T curve gives change in position. So we're doing this all geometrically today,
Why do you
all
call it a
figures.
curve?
Second?
Why do you call it a curve?
Because a general phrase for any function is a curve. Some are lines, but others are curves. But a line is just a curve with no curvature. So by saying curve, you're generalizing. You could say line, but not all functions are going to be linear, right? They're going to be mainly curved. This is an easy one to start, and did it on purpose so you can see the area concept. In a minute, I'm going to get into what if it's curved, what do we do now, right? So that's where I'm going to extend this idea.
Isn't it also kind of the same idea for A versus T, but it's B?
Yeah, very good. And that would be delta V instead of delta X there. Very good. So what we're looking at in 2.6 is the idea that, you know how we went from position to velocity to acceleration? Now, if we go the other direction, we're simply going to say, well, instead of taking the slope of the graph, we take the area underneath. And the area underneath goes from velocity to change in position, instead of from position to your velocity when you take the derivative. So derivative is slope whereas we're going to use this phrase integral soon. Integral is the area under the curve. And that idea of the area of the curve moves us from either acceleration to velocity or from velocity to position change. Okay, position change. So whenever I want to figure out how much a particle is moved, I don't really need an equation to figure it out. If I'm given a velocity graph, I can just calculate the area underneath. Now, until you get to that point in calculus, we're not going to go into crazy extremes. We're going to talk about it with the power rule, because you guys have done power rule already. Did you get into product rule and quotient rule yet? Nice, okay. So you have the ideas down pat. So we're going to see a little bit of the mathematical work in this course before calculus, so you'll have a head start right there. I saw a hand pop up while I was talking, I'm sorry.
I figured it out.
You figured it out? Okay.
I was gonna ask if like this is like a stuff with like the summation or like sigma.
Yeah. So let me draw a curve and then we're going to see the summation appear. Absolutely. So let's draw a new curve now on the next slide. And let's just draw an arbitrary curve like this. Okay? Sinusoidal maybe, something, right? So I just want to have some curvature to it. Your curve does not have to look like mine. As long as it's curved, put some sort of curve to it. Now, let's say that I knew I wanted to figure out, let's say, the position change, not at, but after 5 seconds here. I put my 5-second mark, I put the dotted line, but then here's the problem, right? This is literally the problem that calculus takes on. So you guys already know the first problem in calculus, which is the derivative. The second problem is the integral. This is all calculus is about right here. Can you figure this out? Now, we're going to get into how we can do it algebraically. But how can we approximate the area maybe? What can we do with that area? Think back to geometry class. How do you get an area of something that's not a perfect shape or not a perfect polygon? Chip, what do you think?
You could like draw a bunch of squares underneath, like rectangles underneath the curve, but like make them really skinny so they take up as much space as possible. Like you increase the surface area by increasing
The missing
width.
piece?
Yeah.
So what is he saying really? What is he using? Give me a more general statement. You're right, totally. A more general statement than that.
Break it up into shapes.
Break it up into shapes. Absolutely. What you said is what we're good at, but I didn't jump to that conclusion yet. We're breaking it up into shapes. So theoretically, I could do this to start. Right? Now watch what I'm going to do. I could say the area under the curve is area 1 plus area 2. Ready for this? Plus area 3 minus area 4.
Where this be? Where is that? 5 seconds. Yeah.
Say again?
You say for after 5 seconds. That's for.
After 5 seconds have elapsed. Sorry.
Oh.
Sorry. Thank you. So what you're noticing is that if I want the area, I can figure out A1 and A3 very easily. A1 and A3 are just rectangles. But then A2 and A4, those are like semicircles or sectors of a circle, regions of a circle. So it's not ideal to use circles, right? And that's what we noticed. But in calculus, the idea in the beginning was, let's put any shape on there. So some calculus people would do this, right? Here's what they would do. They would say, let's approximate this with a triangle, right? Take a look. So let's make area 2 now that triangle, and let's get rid of, take a look, watch what I'm going to do. Let's get rid of this piece now, and instead, let's make this one also kind of like a triangle. It's missing a piece. So now we could do this, and we could say area 1 is a rectangle, that's easy, plus area 2, which is a triangle, plus area 2, which is a triangle. Then area 3, well, I'm going to do this. Take a look at what I'm going to do to area 3. I'm going to break it up further. So I can say area 3 is this rectangle plus these two little triangles here, right? Now, based on looking at this problem, would this be an under or overestimation of the area?
Under.
Why under? Yeah, you're missing these little pieces, right? So let's shade what's missing so we can see that. So we're literally missing what's in green. That's the area that we're not considering by adding up the 4 or 5 shapes, I guess. Yeah, we have 5 shapes now. Okay, there's the 5 shapes. By adding up those 5 shapes, A1, A2, A3, A4, A5, we get an approximate area, but it's not the right area. It's an underestimation. Now, if my shape went beyond the curve, we could say it's an overestimation. But then sometimes the shape might be above the curve, other shapes might be below the curve. So you can have overestimations in one area and under in the other. Maybe they balance each other out. But as Chip mentioned, the easiest way to start a problem like this is either what's called a rectangular approximation or a, Max, you've done Simpson's rule yet? Trapezoidal? Trapezoidal? Simpson's rule, sorry, but trapezoidal, yeah. You could also use trapezoids. So imagine, now let's look at 5 to 10 seconds, please. Let's look over here from 5 to 10. And if I wanted to worry about from 5 to 10 here, instead of using rectangles and triangles, I could then just simply use all rectangles and make them really skinny, as Chip said. Okay, and I could put a lot of those rectangles together and add up all those areas. And that is called a summation, right? Sigma, summation of all those areas. Now, I could also use trapezoids. Trapezoids are really nice, by the way. Take a look how nice this trapezoid will fit. Watch this, ready? I go all the way to the top, and then connect the line all the way to here, and drop it all the way down. And look at that trapezoid I just drew. That doesn't miss much area at all. Okay? It doesn't miss much area at all. And the trapezoid does just as good a job as a rectangle. The thing is, the rectangle you can make infinitely smaller. And calculus is all about the limit as delta x approaches 0. As these rectangles get shorter and shorter and shorter, these little gaps that are missing get fewer and fewer or smaller and smaller and smaller themselves. So the underestimation becomes a better estimation as the rectangles get narrower and narrower. Like if I tried really big rectangles, it wouldn't work. So if I tried a rectangle here, take a look. Look at that big rectangle in blue. Look how much is missing. All this area is missing up here. So it doesn't make sense to make big rectangles, because if I make big rectangles, I'm going to be missing a lot of space. But little rectangles only miss little space. So the goal is, again, to make your rectangles as thin or narrow as possible. So in calculus this year, you're going to learn this technique, and you're going to get into the concept of finding those areas. Okay? But I want you to visualize what an area under the curve is. So back to the beginning, the point we were getting at, though, was that the position change, remember, delta x is going to equal the area under the v versus t curve. Okay, that was the gist of what we're getting at in this idea. Rory, you have a question, sorry.
So even though like the trapezoid like visually may look better in that situation, it's like by far
The rectangle is really slim is the way you want to go down the road. And you're going to see that in math. In this class in here, we're going to really get the idea of it. And most of your functions will be, for now, linear. Like going up, going down. So you can fit triangles and rectangles perfectly instead of curved. I'm going to hold off on the curve for a little bit. I can do one or two of them today so you can see it. But there are a lot of rules you're going to learn in calc that would take 2-3 weeks for you to go through. But I don't want to spend time doing all that because you're going to do it in calc anyway. So I want you to start with the idea of the areas first underneath the curve so you visually understand it. So again, that's the first kind of curve. Let's go to the next one that Kara mentioned. Talk about the idea, well, what if instead it's acceleration versus time? It's acceleration versus time. Again, go back to your proof of it. If I want to know how much velocity I've gained, I can start with this formula right here. The most basic formula I've got. And if I want to see what delta V is, solve for delta V in that formula. You just get A times T. And in this problem, if I had a constant acceleration for a given time period, what will happen is, if I want the area under that curve, and make this dotted, if I want the area under that curve up until 4 seconds, the answer is just what? What's the answer? Good, but what's the actual number I'm saying? 80. So what does that mean, 80? Well, it means that my velocity went up or increased by 80 meters per second. So just like the area under the velocity curve showed me how much my position changed, the area under the acceleration curve will show me how much my velocity changes. And that comes right from this equation. Delta V means change. Change in velocity is just the acceleration times time. The height times the width, or the area under this curve. So that's
So like the area under the curve is the magnitude of how much you change, and the slope is the rate at which you change.
sure. And maybe hold off on the word magnitude, because we're going to start to look into negative areas soon too. So for now, we'll just say it's how much it changed by. It went up by 80. Because if we have area below the curve, it's going to be a negative value, so it's going to go down by 80. So be careful with our magnitude for now.
Wait, so let's say like you had like the acceleration equals 10 meters per second squared. Could you find the difference between those two? But then also do the area.
Oh, sure. So and that's another calc question you're going to get to. That's going to be like in the third quarter of the school year. You're not going to get there. It's called area between curves. So if you had a second acceleration here that was 10 meters per second squared, and you want to know by how much do these these velocities changes differ? Well, at this rate, your velocity change would be 80. At this rate, your velocity change would be 40. So when you double your acceleration, you're doubling your velocity change because these are directly related. Absolutely, you can do that, yeah? And you can even see what this area is right here, and that actually plays a role in calculus later on, okay? But not to jump ahead, I don't want to get into too much of that right now. So here's what I want to do. I wanted to give you guys those ideas. But then what I wanted to see you do is just experiment with a cart track with motion detector so you can visualize and see this yourself. So what I want to do is two things. I want you to have a flat cart or a flat track with a cart moving and a motion detector at the end. Okay, this is just an activity. It's not going to be like a full lab like the full lab. This is just to get you to visualize it. That's all it's for. And then what I want you to do is I want you to incline that cart. We did honors physics. I want you to incline that cart a little bit, send it up the ramp, and then let it return back to the motion detector and stop it right before it hits the detector. Okay, so the first time I want it to be a flat cart, and just give it a push, let it go for a while, and at some point in time, stop the motion detector from collecting the data, look at the position change, because it measures position, then look at the velocity graph, try to figure out the area of the curve, see if they match up, if they don't, and why. Now, they'll be pretty spot on, but there might be discrepancies based on the detector. The second time through, though, when your velocity is going up the ramp, the detector is going to measure that as a positive velocity. But then it's going to start coming down the ramp. So I want you to start to think about that a little bit for the second scenario. Okay? Work for now with the person next to you. That's fine. How much time do we have?
We have 8 minutes.
8 minutes?
Yeah.
Shit. We want to do the first one together, maybe? Let's do the first one together, and then I'll have you guys do the second one by yourself tomorrow. Spence, can you grab me the other track, please?
How big?
Either one is fine for now. Just throw it between these two desks right here. That'd be perfect. Alright. So this is what you're going to pretty much do tomorrow. You're going to set this motion detector up again. Okay, so we'll do the flat version together today so you can see it. Okay, so here's how you're going to start. You're going to zero out the device. Let me connect wireless. Does that LabQuest have a Wi-Fi signal on it on the bottom right?
It does not.
It's showing no Wi-Fi?
Yeah.
Okay, hang on. Because I can show on my computer what that is if it actually has Wi-Fi. I'm just going to grab you a different one for a second. It does take a minute to connect to that, so it might not even work for a little while. Maybe hold off until we're done so see what we can use. It should auto connect if that's not the science that Okay, don't worry about it for now. Just connect the device and I'll see. You might be able to manually do it. Is there an IP IP address on there when you go to system? You go to the Wi-Fi, yeah. Yeah, but the problem is connecting to it. The network is actually connected to whatever computer. No, because it has to be the same network my computer's on, then they see each other.
Yeah.
That's the Wi-Fi at school. All right, I'll take a look at that. What we'll do for now, so you can see it, we'll hold it up after. So what we're going to do is we're going to calibrate the sensor. So we're going to choose sensor 0 out, and it's right up against here. M's going to tap the duration. Maybe set it to like 10 seconds, so 5 seconds doesn't run out. Now, what we're going to notice, and I'm personally not going to push this very hard because it's going to go off, and I want it to kind of stop toward the end. And you might have to try this a couple times. So yeah, you start clapping. Yeah. That's way too fast. That's all right. Let's see what happens.
It works the same way.
Position is constant. All right. So for today, guys, normally I would replicate this, but I think it's probably my fault these aren't working. I just did a system update like 2 days ago for all of them, so they didn't need a Wi-Fi. So let's take a look. I know it's tough to see, but the first one here is your position graph. Your position was increasing until it reached the end, and what happened? It stopped, so it stayed constant at the whole end. The velocity, if you look at this, was relatively constant, but it was slowly decreasing. Look at the velocity graph slowly decreasing there. What we can do with these devices is you can actually use statistics on here to actually analyze it a bit better. So I'm going to look only at the velocity graph so you guys can see it a bit better. There's my velocity graph. What I can do is I can find the area under this velocity curve right here. And I can let the graph do all the work for me. So if I go to analyze here, and I think it's under integral, and I can take the integral of velocity, and I can go ahead and I can use this region right here. And what it does is it shades in that region on the LabQuest device. And what does this region tell me? This region, as a sum, comes out to be 0.96. Well, take a look. This is a little over a meter. So if I look at this and I see 0.96 as the integral, and it may not be perfect because I think I missed the beginning part a little bit, but then I go back to my position graph, I can see that it's pretty much at 1 meter when it stopped moving. So the integral of the velocity graph gave me 0.96, and it's practically at 1 meter at this point. So again, proving that the integration of the velocity curve gives you your change in your position. Now, tomorrow what I want you guys, or Thursday what I want you to do when you come in to start, is do the same thing, but have it tilted up so that the velocity is not only positive, but it eventually stops and comes back, and you have negative velocity below the graph. And then I want you to start thinking about what that's going to cause. And you might be able to think about it already. I know some of you are probably already thinking about what the answer is going to be, and that's fine. But I want you to just experiment through that process, okay? I did the homework up already for 2-6. We definitely start that tonight. It's out of Walker, the text. I'm going to put up the multiple choice questions for section 2-6. I haven't done that yet. You guys have the multiple choice chapter 2 document already. It's going to be the ending questions in the multiple choice there, but I have to put the assignment. But the 2-6 homework out of the textbook is already there. I'm going to try to, when I make homework assignments, also put the problem set up at the same time. So today, during 5th period, I'm not only going to put up the solution to the last test for the math problems, but I'm going to add to the problem set assignment for section 2-6. So when you finish the homework for 2-6, maybe tomorrow, the next day, whenever you do it, and then you want to start the problem set maybe over the weekend, you can do that to get a head start. Is that clear for today? Okay? Really good lesson today. I hope you understand what we're doing here. Now, we have not taken the algebraic approach yet at all. So next class, I'll give you guys time to experiment with this on a ramp with different velocities. Then I'll start talking about the algebraic way to do it, and you'll have like a leg up on everybody in calculus. Because it really is useful to at least be able to do it algebraically using the power rule at the minimum. Because that's what most of the functions are. They're either power functions, or you'll start exponential parabolic functions, or trigonometric functions, sine and cosine. Okay, so we'll see how those play a role as well. But tomorrow when you come in, or sorry, Thursday when you guys come in, grab one of these, grab all these materials, and get started right away. Okay?
Clear the data, right?
Yeah, you can clear. You guys can go. Go up and over, guys. Obviously, obviously when you leave quietly though, whenever I let you guys go early because other classes still in session. Yeah.
Can I come in after school?
So what did you notice about the incline problem, right? So let's just draw a quick schematic of this. So it looked like you guys had, well, I'll put the support there. Had some sort of an incline here. And then the cart was here. Okay, the cart's motion was up the incline. It stopped for a moment and then came back down the incline. Right, that was what happened in this. So describe to me rather, what you saw in your position time graph and your velocity time graph. What were you noticing? What are you noticing, Spence? Give me some stuff.
Velocity time graph, it goes up really steep, it goes down like constantly, and then it goes up really steep.
Okay, so what's that up really steep first? So let's put velocity here, we'll put position here. These are both functions of time. By the way, notice what I'm doing. I've mentioned this in class already. Really useful to put your graphs purposefully above one another. Okay, not left to right. And we'll talk about why that is, lining up the times from above. A very useful technique to start with. So in the beginning you said there was a spike up, then a linear function, then another spike, right? So I'm going to draw that sketch because I kind of remember what it should be. Now the velocity also goes negative, so I'm going to extend my y-axis, or my velocity axis. Did my position ever go negative in this problem? No, right? You never went beyond the motion detector. So I'm okay with the first quadrant for the position function. So yeah, the velocity, if you started recording, probably was flat for a little while, then it spiked up, and then it dropped like this, and then it went like this, and then it was probably like squiggly at the end. All right, that was the general shape. What was the general shape of the position function here? The position function, what was it? Just yeah, it was like flat for a little while, nothing happened, and then we saw this, and then we saw this again. Now, where the position function reached a max in my graph is not easy to show. I'm going to assume it's right here. Okay, I know it's not perfect, so just bear with me. Why did I choose that specific moment to call that the maximum height or the maximum position?
The slope there is 0.
Okay, but it looks like the slope of the top is 0 for a couple spots, right? That's what I'm saying. Like, why did I not choose shit right here, or here, or here? Why did I choose specifically that location?
Maybe because it's, if you look at the velocity graph as well, it's the instant where the velocity is 0.
Where the velocity crosses the time axis, we know the velocity's value is 0. So what I tried to do was line this up like that. Okay, so if you want to draw yourself a little bit of a dotted line there, I find, and this can help in calculus a lot too, that when you're doing curve sketching, something you're going to learn at the end of like chapter 3, I think, in your calc class. When you get to curve sketching, it's really useful to vertically line up your times. So it's nice to see that we have a maximum position when the velocity is 0. Yeah. And you guys can take a shot if you want. If you don't mind me showing this. Take a look. If you want to take a shot of your LabQuest device, you can get it really nicely out here. So the graph looks great. Okay, so feel free to do that because the data points you're going to notice will line up nicely. Now, the next thing to talk about. So, for this example, for this experiment, halfway through we know it reaches approximately max height. How is that validated by my velocity curve? Besides what we just showed with the dotted line, velocity being 0 at max height, how is that validated with my velocity curve? What do you think?
Well, because when it's showing the velocity is increasing in the first pushes, and then like as it starts to accelerate negatively as it reaches farther up the track, it starts to slow down. Then once it reaches the top point, it reaches 0, and it starts back the other way.
Okay, so we get an idea, right, that halfway through is about the maximum value, because we see the change in velocity, we see the velocity go from being positive to suddenly being negative, not just because we see it touch the time axis. Good. What else? What else, as of yesterday, I should say, what else could we state that would help us to validate that our position reaches a maximum at this exact moment, or at this exact moment that we're showing here? Yeah.
You can find the integral of the t versus t graph. And
Okay.
That would show what that point at time in the position graph. So it's be like
Go ahead.
whatever that point is, then starts going up. Yeah, you can change the time, but I don't know. Yeah, we 1/2 base times height. So
What did you do it on your device? Did anyone get a number for that? Just out of curiosity, maybe one group can be their value for the integral if you have your lab quest up still. Just M, just the first portion.
Is it N?
It's under statistics. I think. Oh no, it's not statistics. Integral. You have to kind of shade the region, M. I think you have to shade it first.
Yeah, I did.
Okay.
0.488
Okay.
meters.
Now, let's take a look at the array here.
Position is 0.493.
And position there is 0.493. Nice. So the exact moment here where the position height was, you said again 493?
Yeah.
So it looks like, according to our position graph, the cart reached a maximum position of 0.493 according to the position graph. And what we've done is we validated it simply with the area under this curve to show that it's approximately the same. Now, in reality, it should be identical. But what we're noticing is that we're using a sensor, right? And how does the sensor work? It sends out signals and pulses. So every once in a while, some of these pulses could be slightly off. So our velocity function or our position function may be slightly off based on the data recorded. But the 493 to 488 is pretty nice, right? It's pretty spot on right there. So now, that was something we kind of learned yesterday already, right? What we just talked about there. How about the second part of this graph? As a result of looking at the integral, as a result of doing this for a little while, what can you tell us? Yeah, Spencer.
The integral will be like close to the same as negative.
Good. The other area should be close to the same as the first area was, but most likely this area will be a negative value when you calculate it on your apparatus. And what did you get for yours since I used your first one, if you don't mind? So if you can check this right here, from the 0 point for the velocity function to where it kind of tears off again.
Negative 0.49.
Nice. And again, that's meters. I know my units are meters because I'm taking the integral or I'm integrating velocity, which gets me back to position. So I know the units of position are meters, so these area units are also meters. I also can tell because if I actually were to calculate the area, the base is in seconds and the height is in meters per second. So meters per second times seconds, the seconds are going to cancel and then end up in meters. So yeah, so Spencer pointed out here that he noticed when he did the integral on the LabQuest device that the second area became, or was given as a negative.
I get negative. I did the integral on the side there.
Okay. So when I believe Spencer only saw the second half, so it was negative. So as a result though, when you look at this problem and you think about going from start to finish, Spencer, want to finish off what you're saying? What do you end up getting from start to finish? Yeah. The total area is the sum of the areas here, and really it's one value plus the opposite of that value, right? 0.488 plus negative 0.49. So really we're looking at 0.002, right? 0.002, and that would be negative technically. So it's practically zero is what it means, because the motion detector sensed that the cart was going up the ramp, and then when it came back down the ramp, you most likely stopped it probably a little bit sooner than they hit the detector, I hope, right? So there might be a little bit of a delta X, or a change of position from where you exactly started to where you stopped at the end. That's completely normal. But the idea is that the answer should be zero. Because again, from beginning to end in this problem, the change in position is nothing. The change in position is nothing, because it starts and ends at the same spot. That's why the sum of those areas, or the integral from push to stop, should equal zero. Should equal zero. And it might not be exactly anyways, right? Now, again, that's the integral of the velocity curve, showing us that the change in position was approximately zero. And we can see that with our position graph because we end up back where we started. Right? If we look at our position graph here, we see that we started and ended both on the horizontal axis, or both at a height of zero, or a displacement or position of zero to start. How about, yeah, go ahead, Chip.
I was just gonna ask, couldn't you prove that the same velocity area, like taking the integral of velocity in the same area, is just through like a geometric proof?
Yeah.
Instead of like having to,
The problem is right now you guys have data, right?
right?
And the rate at which you increase, right here, take a look, is the function of your push. The rate at which you decrease is the function of you stopping it. There's no way that you have the exact same force in both those scenarios, so this part of the graph is not going to be symmetric. But, Chip, this part is absolutely symmetric because the slope of this line is what? The slope of this velocity curve is what? And the acceleration down the ramp and up the ramp is a fraction of gravity, right? Tell me, what's the slope turn out to be? Can somebody check? It's alright, there's a couple runs up still. Tell me what your slope is for your velocity graph. If you can, and what you want to do is use analyze, fit a linear trend to that. To the region where it's, I think you have to select it first, yeah. We only want the linear region, yeah? Statistics. Alright, so M got a slope, or M's group, M and Kara got a slope of 0.8. So the slope here was equal to 0.8. Now it was negative and it was meters per second squared. So yes, that gives me the acceleration. And notice, acceleration on Earth is around 9.81 or around 9.8. This is only like a tenth of that. Well, look at their track. Their track angle might be at like 5 degrees. And you know already from the concept of inclined planes that as the plane increases, the velocity or the acceleration will get closer and closer to 9.8. When it's eventually vertical, it's a free fall. So if you turn this track vertical and you drop the cart, it's not being supported by the track anymore, right? So it becomes gravity of 9.8 downward, or negative 9.8. So in these problems, we want to recognize here that our slope in the problem is consistent. So there is what seems to be odd symmetry. Have you talked about odd and even functions in pre-calculus? Is that right, Diana? Yeah. So odd functions exhibit symmetry through what we call the origin. In this moment, I would consider this to be like the origin, right? And showing that the graph over here is reflected through the origin over here. So there is some form of symmetry, and in reality, Chip, the values should be the same. But again, because of the push and the stop, you're not going to get the exact same numbers. Yeah. But now on an exam, if they give you data, the goal would be to show that the approximate area, whether you do it with Riemann sums with the rectangles like yesterday, or if they give you an actual function on the exam, showing though that the areas would be approximately the same. Second part to this question. Second part. This is probably the more important part because so far I think this is relatively straightforward because you guys are all good at visually understanding stuff. The second part is this. What do we do when we want to figure out the distance traveled by an object and not the change in position? So I'm not looking at the displacement anymore, but I want the distance traveled. Andel, what do you think about this? What distance? Is that a hand up?
Distance to the max. Distance back as well.
What do you mean though? How do I do that, Chris? You're just in words you're saying that, but tell me specifically what would I do?
Find half the time, which gives you the maximum for the position.
Okay.
And then you basically double it.
So without the velocity graph, we could say, as Chris is saying, well, up here, we've got the final position when it reaches the top of the ramp, and then it starts to come back down. So we could take this number here, and we could theoretically double it if we wanted to. Now, what about with today's lesson, though, or yesterday's lesson? How would I do it then? I don't have the position graph, right? Make believe I don't have this graph at all, which I wouldn't. I would have the velocity data. What would I then do? Okay, so that's right here in the middle. How does that help me, though? I mean, it lines up with the maximum of the position function, but it doesn't. You want to phone a friend? Okay. Chip, help him out.
You just add the two areas together, but take the absolute value of the second area.
Remember how the second area was negative? That's because the motion was down the ramp, right? So the displacement in the second part of this trial was negative. But remember that distance is the absolute value of displacement when it's in one dimension. So really, if you want to find the distance traveled ever, what you really want to do is this. You want to find, and we're going to use this symbol today in a moment, we want to do the integral of the absolute value of the velocity function. I'm going to go through the symbols here up at the top right. But for now, just jot that idea down. For again, for the displacement, we did it already. It was just the integral of the velocity graph. And again, I'll get into the symbols we're using here. Okay, we did the displacement already. We just took the areas and added them together, and we got 0. Because the object started and ended started and ended at the same exact point. But when we look at the distance, it's going to be close to a meter, right? It's going to be 0.49, 0.488, which is the first area, plus 0.49, which is the second area. Okay, 4949 is going to be 98, right? So 978, I guess. So again, I'm adding the absolute values of those two quantities to get the distance traveled. So the integral gives you the change in position. But remember, the change in position can be a positive or a negative quantity. If the displacement is positive up the ramp, it's a positive quantity. It's down the ramp, it's a negative quantity. But if I want distance, I want to consider that I want the absolute values of those displacements separately summed together.
So by distance, you mean like the distance total, like total distance?
Correct. So up the ramp, about 0.47, whatever it was. Down the ramp, about the same. So I add those two values together. It's like, remember in physics last year, if you talk about walking around your circle and you know where you start. What's your displacement? But your distance traveled is the length of that curve, right? That's what we're talking about here. So the displacement is absolutely 0 because you end and start where you end and start in the same position. Okay, now, follow-up question for you. Follow up. So, this problem is the integral of a velocity curve. What if instead of a velocity curve, I use a speed versus time curve? Speed versus time. If I look at a speed versus time curve, what can that tell me? What can that tell me about the problem?
It gives you the absolute value of velocity.
It does on the graph, yep.
Makes it easier to add it together.
So as a result, what can I gain from a speed versus time curve? What can I gain from a speed versus time curve versus a velocity versus time? It's very limited in what you can gain, Max.
You can only get distance.
You can only get distance. Let's think about that logically. A speed versus time curve, notice how I drew it? I drew it this way on purpose. Because what's it never going to have?
Negative.
Negatives. So a speed versus time curve for this scenario, ready for it? This is what it is. And actually some of you could predict it if you want to draw it on your own graph first. What should it look like? Draw it on your own first, take a minute, and then let's see if you have an idea. Think about speed versus time as opposed to velocity versus time. If speed is always positive, what should we just do with the graph that's below the axis? The part of the graph that's below the axis, what should we just do with it? What's the one word? What's the word for that?
It's a reflect.
Reflect it. Very good. Reflect it over the horizontal axis. So that's what the beginning looked like, right? I should actually draw it a little bit smaller, I guess. So it lines up. And then instead of continuing downward, it now goes like this. Okay, I know it's not perfect, but do your best here. Take the green area and reflect it over the horizontal axis. That's what the speed would look like for this option. And think about it logically, right? You give it a push, right? You give it a push so it has max speed. Then it slows down, slows down, slows down, slows down, and stops. That's where it hits the time axis. Then it speeds up, speeds up, speeds up, speeds up, speeds up, speeds up, speeds up. Then you stop it. And when you stop with your hand, that's right here now. And your hand is now stopping and giving it an applied force, causing it to decelerate.
Yeah. In the first little bump there,
It should be symmetric.
It should. Okay.
Yeah, it should be symmetric. That's what I'm
And
saying.
it should be the same kind of shape as the B versus T, right?
Yeah, it's actually the same shape as above. I'm just not doing a good job of getting that in there. Sorry.
Sorry.
That's okay. So that would be like that one, yeah. Now the second one, I'm having trouble. Let's see. I guess it would be the exact same reflection over that. And then it would look like that. Yeah, right? Something like that? So yeah, these two areas summed together would both be positive values. So here's the thing. If you know the scenario, like this is a ramp, right? With a cart going up and down. If you know the scenario and you know the context of the problem, you could also get the displacement, not just the distance. Like for example, if I knew this was going up a ramp and then back down the ramp and I had a speed curve, I would know that this part of the graph is really on the bottom because I know the context of the problem. But let's say on the exam, this is what you're given right here. You're given a speed versus time curve. You don't really know what's happening. There's nothing you can say that like, oh, I know that it was gaining displacement in a certain area. You don't. Because maybe this part of the graph is also below and both of them flipped up now, right? So as a result, giving only the speed versus time curve, I don't know which part of the original graph of velocity was below the axis. So I cannot conclude anything about displacement. I can only conclude that the integral of a speed curve will always give me the distance traveled. Now, for all of these integrals, I haven't put anything yet because we're going to get into that in a minute, you need to put what are called limits on them. And limits simply mean from where to where. From where to where. So I might call this T1 and T2 over here. So it would be from T1 to T2. Okay, so let me show you that on the integration for the speed one. So if I'm doing the entire thing, that's T1 and that's T2. From the beginning to the end, the areas of all those regions summed together from T1 to T2 is this concept of the integral. And that's the distance you will physically travel. So far, so good? Is this pretty reasonable? You're going to be way ahead of your classmates in calculus because you're not going to learn this until like the second part of the year and you're going to start talking about net change theorem. And that's what we're doing right now. Net change. Net means total overall, right? Whatever we're looking at, the sum. And we're looking at the change. Here, the net change of velocity gives me displacement. The net change of the speed curve gives me distance traveled. Right? So I see that those values are different, but they're still giving me a net change. Net means overall. What was the overall change of this curve? Well, if it starts and ends in the same spot, the overall change should be 0, and it was very, very close to 0 according to our data. Okay? Now, yesterday I quickly alluded to the concept of acceleration. Let's quickly reiterate that idea. For example, what we're going to do is we're going to take a look at the acceleration graph. And if we have an acceleration graph versus time, and this would have to be a scenario where you have a variable acceleration. So those three formulas we used in the last chapter, those three formulas, x equals x0 plus v0t plus 1 vt squared, v equals v0 plus at, v squared equals v0 squared plus 2a delta x. Those big three. What was the assumption you made when using the big three? What was the assumption? That a was constant. So, for acceleration graphs, if you're given anything that's not a flat line, you cannot associate this problem with the big three. Is that clear what I'm saying here? Okay, you can't use the big three to solve a problem if the acceleration varies at all. So, a simple graph, like we showed yesterday, we looked at this graph yesterday and we said, well, what if the acceleration is -10? Let's say it's on the other side, sorry. What if it's -10 and it's just gravity, right? And we're under the force of gravity for, 6 seconds. Well, then we can do what we said. We can put a little dotted line here. We could find that area. And we could say, well, our velocity change is going to be 60 meters per second. That's how much velocity is going to change by. Because I'm getting the area by simple multiplication. So for a constant acceleration problem, this makes sense, this answer. Because if I think back to my formula, here's my formula. And then look, here's what I get. And that's exactly this right here. Take a look and make sense of it mathematically. It's not clear to you. Delta V, the change in velocity that we gain from this acceleration, is the area under the curve, right? So that's the change in velocity. But delta V is V minus V0, which equals AT. And AT is really A, right? A is the height of the rectangle, and T is the width of the rectangle. This is -10 times 6, yielding -60. So if I use the big three, It's only valid when the acceleration is constant. So as a result, the moment I don't have a constant acceleration, I've got to start thinking about, instead, the area under the curve. So the area under the curve for this graph here, remember, gives me the change in velocity. Not that formula. Again, you're not going to use this formula here because the acceleration isn't constant. Now, where would this help? Multiple choice problems, a lot of the time, have a tendency to ask questions such as this. Velocity of the particle to start is 3 meters per second. Find the final velocity after a time interval of blank. Now, if I started with a velocity of 3 meters per second, and let's say hypothetically that delta V value is 107 meters per second. That's what the delta V value is there. The area of that curve is 107. If that were the scenario, and I started with a velocity of 3, my final velocity is just the sum of those things. Think about that logically. Normally, I would use this formula right here. Agreed? Instead, watch what I'm going to write. My final velocity is my initial velocity plus the area under the acceleration curve. It's really the same formula, actually. It's just that integral of a, that little symbol of a, when it's a constant a, becomes just a. And the dt becomes the t. Take a look at that formula at the top. I know it's not mathematically sound, so Max is probably saying to me right now, Mr. Howe, it doesn't actually become that. But the points actually do line up. This is like your acceleration. And this is like your time period, dt. It's a very, very small time period. It's called the differential time. But the idea I want you to see is that this a right here is really this right here. This dt is really this t right here. It's just that this equation is actually a simplified form of up here. The simplified form is like, oh, if the acceleration is constant, we don't gotta go crazy and use this integral up here. There's no need for it. So let's use a simplified form when the acceleration is constant. So jot yourself a note about this stuff, that these are the same formulas really. But the second one makes the assumption that acceleration is constant, where the first one has a variable acceleration. A variable acceleration.
So when would you use this in a question? What would the question ask?
The question would have to give you a problem with either one of two things, Kara. A graph of A versus T, and that graph cannot have a constant A. If it's a constant A, it doesn't make sense, right, to use the blue one. So it's either a graph, I guess 3 ways, actually, say 3 ways. Give you a graph, it could give you the equation for A versus T, or A of T, the acceleration function really it could give you, or it could give you data. It could give you data points, and you'd have to plot those data points and assume connecting with a curve and trying to then find that area. And we're going to talk about how to do that, and in calc, we're going to talk about how to do that with only data. Where you could use that rectangle law, the Riemann sums we're going to talk about, or you're going to talk about. Okay, we can use Riemann sums or trapezoidal method, either one really. But you'll most likely use Riemann sums for this. Okay, so again, that's a great question. See what Kara asked there? Really good question to think about. When are we going to use this? Not, oh, Mr. Howe, how do you use this? But when? When is the most important question in all physics? Alex and I spoke about this the other day. He recommended, and I think I will do this, that at some point I start giving quizzes on set up the problem. Not get the answer, just quizzes on setting up the problem. Because you guys know that from your first test. The math was not that hard really, right? It was just the setting up of the problem that becomes the most difficult part. So asking yourself questions such as, when am I going to use this, is really, really vital to knowing what to do on the test. Because right now, we've only studied kinematics, right? Once you get the whole slew of the year under your belt, now you have to pick and choose from every problem. Is this a kinematics problem? Is this an energy problem? Is it an angular momentum problem? Is it a linear momentum problem, right? So the question of when do we use this idea is when we have an acceleration function, either graphed with data or the function itself as an equation. That's when we're going to use this idea. And when we're looking for most likely a change in velocity or a final velocity given the initial velocity. Okay, but the idea here I want you to see is that the acceleration curve behaves very similarly to the velocity curve. Just that when we integrate this, we get velocity instead of position. So my general schema I want you to think about right now, what we should be thinking is this. Right? That's what we know. Take the derivative and you move down. But instead now, we're going to start saying we can take the integral to move back up. That's the general idea you should start thinking about. That's the order in which we're going to be moving. Position, velocity, acceleration. And then we go back by using that term integral. And we're going to use the phrase antiderivative today to really emphasize that the integral is just the opposite of the derivative. That's all it is. And we're only going to focus on the power rule. In your calc course, you're going to do a lot more integration, and when you get to that, that's fine. But for the sake of this course right now, most functions on the test are given as polynomials already. Those that aren't will come later in the year with like oscillations. Those become sine and cosine waves. And you'll learn about that in calc before we get to it here for sure. So I'm not concerned about that as much. But I want you guys to see that this, another word for it, is antiderivative. Antiderivative. So, when I think, and I'm going to get into the rules now for this. When I think about this function, what's my power rule for derivatives tell me to do? If I want to take the derivative of this function, what do I physically do?
N x n to the power of n minus 1.
Yeah, and can you tell me in words what that means?
The number, when you take the derivative, the number the exponent is basically times the variable.
And then do what to the exponent?
Subtract 1.
Yeah. So always bring down the exponent, subtract 1 from the exponent, right? Bring it down, subtract 1. That's the power rule that you guys know in your calc course. So, I've got a question for you. If I'm doing the antiderivative, I'm going to do the antiderivative. Again, the derivative was bring it down and take it away from the exponent, right? So multiply and then take 1 away from the exponent. How might I get the antiderivative? What are you thinking, Chip? Yeah, go ahead.
Maybe you would do like, so you would have your derivative, and then you take the whatever, you look at the exponent, you add 1, and then divide n by n plus 1.
Yeah, I like that, but not n plus 1, just n.
I would just,
Because this is going to turn into n when you add 1 to it, right?
right.
So this new exponent becomes n, and good. And you divide by the new exponent. Well done, Chip. And the idea behind it to see is this. Ask yourself this question, people. If I wanted to go from here to here, how would I do it? That's the question I ask yourself. Well, what would you do? Technically, to get back to there, you would add 1 to this, wouldn't you? And would this become n? And how would you get rid of this n? You would divide by n, wouldn't you? And isn't n the new exponent you get when you add 1 to this? So the antiderivative, instead of bringing down the exponent and then dropping it by 1, we're going to instead increase the exponent by 1, and instead of multiplying by it, we're now going to divide by it. So let's do an example or two to see that. Okay? So if I start when I tell you that the velocity is equal to simply t squared. The velocity function is equal to t squared. I want to figure out the position function for this. And the position function is the integral of the velocity function. As a result, I want to increase the exponent. So obviously it's what order or what degree is this polynomial going to be now? Good. And then I'm going to divide by the new exponent, which is clearly 3. Now, in a moment, I'm going to talk about this idea of a constant at the end, plus c. But for now, don't worry about that little plus c there. I want you to recognize this part here. So go ahead, if it's not clear, take the derivative of this. Take the derivative of this. What do you get when you take this derivative? Mondell, what do you get?
Just t squared.
Yeah. And that's from here. Because the derivative of position should get you back to velocity. So again, taking the derivative of this position curve proves to you that you got the right answer for your integral. Because again, the 3 comes down, the 3's cancel, and this becomes a 2. So t to the second is t squared here. So again, take the derivative. What's the derivative of a constant, people? 0, right? Everybody agrees with that? So why not take the derivative of this? Doesn't it just drop off so we don't worry about it much? That's really intriguing if you think about that. So where's this constant coming from? Where's that constant coming from? Max, what do you think? Let me help out the class. I know you've done this already. I know you're not jumping the gun. I appreciate that. But for this sake, where does that constant come from, Max?
Like you never know if it'll be there. Like it doesn't happen.
Why, Max?
Well, and then when
Take
you
the
take
calculus
proper,
approach. Take the physics
when you take proper, okay.
The calculus approach is any number could be there because when you take the derivative, you get back to 0. So it's 2, 3, 4, 5, 6. Doesn't matter because it's constant. How about the physics approach? What are you thinking?
Because it's like the starting point of the whatever.
Of the what? What was it called?
What's the starting position?
Good. The position function. What does it always start with? X equals x0 start plus v0 t plus 1/2 at t squared, right? That x0 in the beginning. This is just, hey, you know what? We don't know where the position function started. Maybe it started at 2 meters. This becomes a 2. Maybe it started at 3 meters. It becomes a 3. So this constant, when you integrate velocity, is really just x0 every time. So when you find the position function and you integrate velocity with respect to time, you end up getting really some quantity here plus the initial position. Always going to get the initial position as an extra value or a constant at the end. I don't want to delve too much into the idea of constants and families of functions because you're going to see it in calc, but it's not as important as recognizing that you're always going to get this, the initial position. The initial position. Always going to come up. And I promise you I'll revisit it, and we'll talk about why it's the initial position and not something else. But you're always going to get something else at the end when you integrate velocity, and that's your starting point always.
Could you like really explain those
Yeah.
two equations?
So if I were to think about this equation, let me just put another equation up to help. If I were to think about this equation, okay, right? And look at that equation. What I notice is that every position function starts at some initial position itself. It could be 0, and this might be 0 sometimes, right? So like the Betty-R thing, one was at 0, one was at 120, whatever the number was. So this could be any value. Now, based on the velocity alone, what do we gain from integrating? We know that we can see the change in position, right? That's all we know from integrating velocity. It's the change in position. And we did that a couple slides ago with this. We saw that the integral of velocity became 0 because the change in position turned out to be 0. It ended and started where it was in the same spot. Now, that's the change in position. So really, is this change in position x? X is just position alone, right? So really, move the x0 over here, and you really have this in the formula. This is really the way the formula is written. We just write it nicer to make it easier for us. And what do we see on the left side? That's change in position. So when I integrate velocity, and I say to myself, oh, I'm getting the current position, I gotta know where it started, because really, this is a displacement function in reality. So this is just like taking this x0 and subtracting it over here, and that'll be the current position minus the initial position, which is the change in position, which is equal to the integral of the velocity curve. Let me write it one more time for you in a different way. So I'm going to put it at the top right. So here's what I'm going to write. I'm going to write it as this. I'm going to say that the integral of velocity, dt, is equal to the change in position, which is what we just covered from the ramp. As a result, I could say the integral of velocity, dt, equals x minus x0. And then what can I do with the x0? I can add that over to the left side, and it becomes this. And if you look at this, this is what I'm trying to say right here. You're always going to have some other quantity added on. And the idea behind it, Tristan, is that if I were to take the derivative of this, I get back to the velocity function I started with. Like the derivative of this guy gets me back to here, right? But what's the derivative of a constant anyway? It's nothing. So that nothing is still here. It's just plus 0. It's there. You just don't see it, right? There it is. So technically speaking, Whenever you differentiate a constant, you get 0. So when you integrate something, you got to tack on a constant at a time.
Okay. So
You're gonna
in
get
the
it-
case of position, the constant would be the initial.
Correct. And what do you think is going to happen next? What am I going to go to next? I just did velocity between position. So I've done velocity and position. What other integral can I do?
Acceleration velocity.
And what do you think what do you think the constant will be for that?
The initial.
Yeah, very good. V0, hold on. So the idea behind this is that we can take this idea and extend it now and get V0 as our constant for the acceleration curve. So let's take a look at that down here on the left. So we've got, let's say the acceleration function. Let's just say it's gravity. Make it simple. Let's say the acceleration function is just -10. Okay, approximate gravity. The acceleration function is -10, and I want to find the integral of that. I want to remember that the integral of acceleration function is going to give me the change in velocity. The change in velocity. But by definition, change is final minus initial. Final minus initial, v of t. I'm putting the actual function. So then I would add over the v0 to this side. And I would get, well, it's just really v0 plus the integral of at dt. So really, again, what are we doing here? We're recognizing that this constant at the end here, once we integrate, is going to be your v0 value. And some of you are probably saying right now, well, when I integrate this, I'm going to get another constant, and a constant plus this. Well, a constant plus a constant is still a constant. And that's something weird in calculus I learned later this year. That you might have problems where you have two constants multiplied, C1 times C2. It's just a new constant called C3. You'll see that in a couple of months, actually. But I want you to get the idea down, Pat, that when you integrate velocity, integrate acceleration, you get the velocity function. But you have to tack on the plus v0 because of the constant. So let's see an example. Let's use -10 for our example here. Let's use -10 for our example here. So if I integrate a constant, what does it become? If I integrate a constant, I know this is a weird one, right? What does it become? Ask yourself this question. What do you have to take the derivative of to get a constant? Of x, very good. Like 3x. What's the derivative of 3x? So what's the integral of 3? You follow how that works then? And I'm only doing the power. That's it. And you're only going to learn it with me, the power, right now. Because I don't want to make this a calculus course, which it could be easily, right? You can tell how related they are. So the integral of acceleration of -10 becomes the velocity curve when I integrate it. Let me actually write that out so it makes it simpler. Hold on. So the integral of at dt, and again, the dt just means I'm using time as my independent variable there. The integral of this will become -10 times t plus some constant again. Again, if you're not seeing it, take the derivative of this function right now. Take the derivative of -10t plus c. You'll get -10. The c drops off, its derivative is 0. The derivative of a linear function is simply the slope. Derivative means slope, right? Calculus, derivative means slope, which is why when we take the derivative of a linear function, the answer is always just going to be the slope itself. So when I take this derivative, I get back to -10. When I take this integral, I get up to -10t plus c. But again, as Tristan said, Tristan, what is c in this problem?
Oh, c is the initial.
Good. C is your v initial. So it turns out that we want to make a point to write this down. That whenever we integrate acceleration to get velocity, we can get the velocity function, but we have to consider the fact that we have the initial velocity also. And the same thing goes for integrating velocity to give yourself position. You have to put the initial position there as well, which is this x0 over here in red, which is the x0 value. I want to kind of summarize this so you guys can see it a little bit better, and we'll make a table to see it, okay? Actually, maybe I'll even use this table. I have a table written down here. Let me see if this is worthwhile. And what I'm going to do is, I gave you guys homework already. And the homework I gave you, if you recall from Walker, if you looked at it, is mainly graphical stuff. It's mainly graphical. Because according to Walker, the way they approach the text is that you're not going to really learn derivatives as much, I guess, yet, and you're going to do it all. But I want to also give you functions to practice, but they're going to be power functions, okay, or power rule, polynomial functions for the power rule. So what I'm going to do is, your second homework is going to be like an actual document. Honestly, I went through the internet and put together a ton of problems on derivatives and integrals, all regarding physics, all using kinematics. So over the weekend, what I want you really to focus on, Walker for sure, do the problems, they're useful. And you'll get the net change and do the area of the curve, that's good practice. But the document I put together it's rather lengthy. Just explore it, start going through it, see how much you can get through over the weekend. If you want to get through the whole thing and practice the whole thing, that's great. But you could start over the weekend and maybe finish it throughout next week, so you get a little bit of review for this. I'm going to put up that document, though, or the image from it. And the image I put in the very beginning, again, none of this is mine. So I literally went online and copy and pasted images left and right. And it was really quite useful to do this. So this image, let me put it up on the board so you guys can see it better. It'll be at the start of this document so you can see it. So it might be a nice reminder. Okay. Here's what this image is going to look like. Okay? And it really does help if you look through it. Okay, it organizes all the concepts that we're really talking about with kinematics. So, we start by asking ourselves, if we want to find the position at any given moment, we can look at the position graph and just get the y coordinate. Alright? I can just look at the position graph and get the y coordinate. That's the first thing I can do. Actually, should I? Hold on. Let me import this onto the slide so you guys can see this later on. I know this is ridiculous, I'm taking more time, but you're not going to be able to see what I'm recording there, so I want that to be available for you. Here, let me do it this way. Hear what I'm saying if you look at this video later. So, if we want to find, by the way, this is the position column. S, they're using S for position in this table. X or S is fine. V is the velocity column, and obviously A is acceleration here. If you want to find the position at any moment, you could simply look at the position function and look at the y coordinate. That's one of the first ways to figure it out. But what you could also do is you could say, I could find the displacement in order to give me the position. If I know where I start and I know what my displacement is, I'll know what my position is after undergoing that displacement. So the second way of getting the position is to take the displacement, which is really the area between the curve of the velocity curve and the t-axis, the area of the graph or the area under the curve there. By the way, area under the curve, it's not a misnomer, but keep in mind that's not always under the curve, right? Because when we were on the negative part, it was actually above the curve technically. It's the area between the curve and the horizontal axis is what they mean when they say area under the curve. So the area between the graph or the curve itself and the horizontal axis, that will give you the change in position. If you do the integral, again, of Vt, that's what this is the integral of Vt, that'll give you the change in position, which is the displacement. You could then take that displacement and add it to your starting position to get yourself the current or instantaneous position. You could obviously also just say to yourself, how do you find displacement? If you have the position graph, just look at the difference in the two y coordinates. If I know the initial position and I know the final position, I can see how far they've changed, so I could use simple algebra to do it, or I could use calculus to do it. Then when I get to the next one, when I want the instantaneous velocity, I can take the slope of my position graph and find the exact tangent slope at that moment to get the instantaneous velocity. We did that a week and a half ago already now. Or I could simply look at the y-coordinate of a velocity graph to give myself the velocity at any instant in time. Finally, again, I get to the next part, which is the same concept. If instead of the displacement, which is the change in position, I want the change in velocity, I can get the change in velocity by looking at two different velocity coordinates and subtracting the two. Or I could do the integral of the acceleration, which is the area between the curve and the x-axis. And then finally, if I want the instantaneous acceleration, I could take the slope of the velocity graph, which is shown here, or I could find the y-coordinate of the acceleration graph, and that'll give me the acceleration at that instant, at that moment. Yeah?
When you get the change in velocity from the position graph, if you did the instantaneous velocity at the beginning and then the end, and then did the slope formula?
If you did the instantaneous velocity at two different locations, you're asking?
Yeah.
So if you found the slope at one spot of a position graph, found the slope at another spot, and you want the change in velocity, sure, you could. Absolutely. Yeah, because it's not listed here, you mean? Yeah, you absolutely could. Good idea, Max. Now, that might cause a problem if you're trying to figure out, let me think for a sec where that could be an issue. You get the change in velocity, yeah, which could give you the average velocity by finding the slope between those two values, right? The two values subtracted over the time period subtracted. I'm trying to think if that could cause a problem down the road if there's an issue where that would be true. No, because even if it's a negative slope, right? I'm trying to think of all the scenarios. A position graph that does this, positive slope, negative slope, indicates positive velocity, negative velocity. The difference between like 5 minus negative 3 is going to be 8. It's still going to be the right answer. Yeah, good idea. You hear what he's getting at there? Does that make sense? So to find the change in velocity, if you want to really look at that, you can do the derivative of the position function evaluated at the first position minus the ddt, not ddx, sorry, ddt. You could find the minus the derivative of the position function evaluated at the second position, x2. So you can take the derivative of the position at the first position minus the derivative of the position at the second position, because this will give you the slope of the tangent, which is the velocity 1 minus velocity 2. You could absolutely do that. Good idea, Max. Good addition to the table. Anything else we could add to the table that we're not seeing?
Is that the multiplication?
This is ddt
Yeah.
of x evaluated at x1. This vertical line you're going to use a little bit later in calc. It means evaluated at, and that's the location you're going to evaluate it at. There's a lot of ways to write evaluated at. That's just one of the ways to write it. And then this is a minus here in the middle, and then the same thing at the second position. I don't know if there's anything else from the table that we could add that would help us. Max, that was a good addition. I'm trying to think if there's something else.
You can do the instantaneous position by subtracting the displacements after you take the integral.
Find the instantaneous position. Once you do the integral of the velocity curve, you're saying? That is kind of what this is saying, though, I guess.
Yeah.
Right? The area between, you add that to the initial position to get up here. Yeah, so again, you could do this, right? You could say that the instantaneous position is where you started plus the integral of your velocity curve. And that's what we kind of wrote on the previous page. Yep, good idea. And what Max is saying really is it's saying, well, take the displacement, which is this integral, and add the starting position to it to get the instantaneous position. Okay, so if you want to highlight.
How do you find that?
Which one?
No, the second one.
So this right here is really this right here. That's what that is.
Okay.
So the area between the curve is the change or the integral of the velocity, and then you add the starting position to that, you can get the instantaneous. How do you get it? Again, a function, a graph, or table of values. One of those three things has to be given to you. It's not just like it appears out of nowhere. Yeah, you have to be given that information. You know what calculus and physics exams like to do? This is a good test prep for you guys. Here's what they really like to do, which is kind of like annoying, but it works and it makes sense. Ready? Here's what they do. They say this. If the following, if the integral of velocity from 3 to 7 seconds dt is equal to negative 20 meters per second, let me just make this a little smaller so I can fit it all. Determine x of 7 if x of 3 equals 4. This is the kind of question I like to ask as like a multiple choice. And it seems really complex because of the symbols, because of what's going on. So at first it's very like, oh man, this is a tough problem. But if you understand the concept of the integral and that change theorem, it's actually the easiest problem to test. The integral of velocity gives me what again? The integral of velocity gives me what? More specifically, delta x, the change in position. So the change in position from 3 to 7 seconds is how much? Oh, I put meters per second. Sorry, thank you. The integral, or the change in position, is clearly negative 20 meters. If I started, though, at time equals 3, at a position of 4 meters, if I started at a position of 4 meters, I would simply say, I'm starting at 4 at 3 seconds, And once I get to 7 seconds, I'm 20 meters behind where I started. My change in position is negative 20. So I'm all the way over here, really at negative 16 now. So again, this graph is showing me that when the problem started, at time equals 3, my position on the x-axis was at a position of 4. That's what this is saying in the beginning. That's this guy right here. Now, what they're saying next is that from 3 to 7 seconds, the integral of my velocity, my change in position, is down by 20. So really what I need to do is I need to extend this graph and go down by 20 at a time of 7 and put my second coordinate down here at negative 16. Now, do I know what happened in between on the graph? It's a great question for us. Do I know what happened in between those two times? Give me some.
I mean, you have to know that between 4 and negative 16, it's at every distance in between, but you can't tell when.
You see what Chip is saying? I would have to be given a ton of these little integrals, 3 to 4, 4 to 5, 5 to 6, 6 to 7, to know what's physically happening every second along the way. So this information in the beginning of the problem only gives me the starting position, the change in position, and therefore the final position. It does not tell me anything about the curve in between. It could be a linear function. It could be all wiggly. It could be crazy. I don't know what it is. It could be a sinusoidal decreasing wave, which would look like this. It's a sine function multiplied by negative x sine x, where the sine curve just drops down every time. It could be any of these things, but I do not know what it is because I don't have the information. So on the exam, they will give you the information necessary to answer the specific question, although it may not specifically give you all the information about the motion of the particle itself. Okay? Again, what I want you guys to do over the weekend is this document. Let me give you a quick insight to see it again so you guys get an idea. It is lengthy, so I'm not saying you need to do the entire thing this weekend, but I'd like you to get a start on it so you're used to these problems. So here's what it looks like. So I give you the table first, then I do a bunch of just free response questions. This looks like multiple choice. It's not multiple choice. These are part A, B, C, D. So free response, the numbers, ignore the numbers. Again, I copy and pasted a lot of this, so the numbers aren't going to be right. So then it goes back to number 1 there. Okay, number 2, back to there. Then about 7 free response problems. Then 3 scenarios of free response, which are really intriguing. If you can get these ones, you'd be really confident in your work. But this is the end of the free response. Then I do a bunch of multiple choice practice problems for you. Okay, and the multiple choice practice problems all have to do with integration and derivatives again. So it's combining everything we've done with integration and derivatives for 1D kinematics. It's 8 pages length. So if over the weekend you want to do the first 4, and next week do the next 4, that's a nice way to break it up to think about this. Okay? Really good review for the AP exam. Also, obviously, because we really got into integration here, on the next test, you're going to expect there to be integration. Right? We're going to end with this or begin the next test with this section, and in our next class, we're going to pick up with projectile motion. So we're kind of done with one-dimensional motion at this point. Is that clear? We're going to get into projectiles, fire, and angles. So again, over the weekend, start to look at this stuff. If you can, I know the bell rang, but if you can, just try to collect stuff if you can before you leave. I'll put stuff on. If for some reason you didn't turn in that lab, make sure that lab is in at this point. Okay, we're talking about the labs that are due today. I'm not a big stickler about being a day late for stuff like labs. If you need the time, as long as it's not a consistent thing that happens all the time. You guys have class like that or no? You all free next period? No. Say, if you have class, they're gone. If you have free, try to put stuff away if you don't mind. And if you have free, try to put the gadgets away. If you have class, go to class. It's not a problem.
Are we proper to assume this equation for finding the integral from the derivative?
Yeah, very good.
Okay.
Integrate and divide by the new integral.
Yeah.
Other direction. Make sure these devices are shut down, please, before you get them back.
Are you ready?
What? Do you have something? They're fucking stress balls.
So that's my only period free on. I have the period before I teach, and then I teach the next 2 periods after. So honestly, it's probably not a good time. Is there any other time period you have
I
at
got
all?
I put in the morning because I cross-checked their schedule. Nothing.
You just want to go over your test? Is that
Yeah,
all it is?
pretty much, yeah.
Let me email you back. Let me look.
Okay. No, that's last year.
I know, what?
I have no idea.
Let me look at my schedule and get an idea of what's that. The only other option I have is and you haven't practiced at the school today? I recorded it purposely because I knew you were here. And so the first 20 minutes they did the experiment with the ramp, but I put it all on the iPad so you can see the video. Okay? All right, Bruce, thanks. I'll email you back. I watched from the first inning to the last inning. It was such a good game.
Last year we had no.
I'm sorry. Yeah, it was really sad. I feel bad for Owen. He's probably depressed.
He's so sad.
He's got to be. I mean, that was like the one series that was like a lock. Everybody was saying, "Oh yeah, the Nationals. They're not going to be anything, right?"